Greetings and welcome to Organic Chemistry. In this very first video, we will be discussing some review from general chemistry about atoms and their electrons, specifically talking about core electrons, valence electrons, and a little bit about Lewis dot. I would like you to try some of the problems I listed, and if you can, you probably don't need to watch this video, but if it's a little bit foreign to you, or if you feel like you need a little bit of review, please by all means proceed. Take some notes on these videos if you'd like to. Remember, you can pause them and rewind them or anything like that, and save your questions, write your questions down, and I will gladly answer them in class. Alright, so you may remember from general chemistry that when we're talking about atoms, we talk about the general three subatomic particles, which are protons and neutrons and electrons. They all go together like this. We have protons, the center of an atom, as well as the neutrons, which are also in the center of the atom. So we call that combination of protons and neutrons the nucleus. We then have electrons in some type of space around the nucleus. Electrons are often written as a lowercase e with a negative charge. Therefore, what we'll have in any given atom is a positive charge located here in the center, in the nucleus, because the protons have a positive charge. The neutrons have no charge, therefore we will always have a plus charge in the nucleus. And then we will have low mass electrons that are always in some type of motion, but just kind of consider them to be located in a cloud outside of the nucleus. As you may have gathered from the title of this presentation, what is most important to a reaction in organic chemistry is going to be the electrons themselves. The protons and the neutrons are stuck. They don't go anywhere. They don't move as a reaction goes on. So essentially we can't change those, so we don't really worry about them. They are important. They are there. They give the atom an identity, but it's the location and the movement of the electrons that gives us an organic chemical reaction. All right. So let's then look at where these electrons can show up, both in terms of physical space and in terms of energy. So the locations or areas, these clouds where the electrons can show up, are called orbitals. Each orbital is a separate, think of it as a separate kind of parking space. These are separate locations where electrons can show up, and you may remember that 2 electrons can occupy any given orbital at a time. We have different shaped orbitals. We have s orbitals that are shaped like a sphere. We have p orbitals that are shaped more or less like a propeller or a peanut. And then there are also d and f orbitals, but thankfully in organic chemistry we don't get to atoms that big, therefore we don't worry about those very much at all. Alright, so with the s orbital you can fit 2 total electrons because there's only that one orbital. With p, it gets a little bit funny because every time there's occurrence of a p orbital, there are actually 3 p orbitals that exist simultaneously. And these are one that is more or less up and down, one that is more or less side to side, and one that is, and I'll do my best art skills, coming out at you and going backwards. So the 3 of them more or less go together to look like this, where there are lobes sticking off in every direction. But if you count all of those up, you'll find that we have, with any given p subshell, that is this mixture of p orbitals, we have 3 p orbitals in more or less an x, y, and z orientation. Therefore, since each orbital can fit 2 electrons, we can fit 6 electrons into a p subshell. All right? So, the way that we fill these, and this may look a little bit more familiar to you, is that we fill one s, which we write in a low energy. All right, so here's my energy. All right, that's a low energy orbital, and one s would fill first with electrons, followed by a higher energy orbital, which would be 2s. All right, the difference between those two is size, and also there's nodes, but effectively think of it as size. After the 2s is also full, then we begin to fill up the 2p. And there would be 3 lines, or 3 orbitals for a 2p. So essentially what I'm showing you here is In the top right, these S and the P's, these are the shapes of the orbitals, which will be very important, but also thinking about the energy of these orbitals is also important, as the electrons will always go in one at a time, and they will be found essentially in the lowest energy orbitals possible. All right. So we write these electrons as little half arrows. All right. So if you've got a given atom that has 2 electrons, you would find both of them in the lowest possible orbital, which would be 1s. If you have something with 3 electrons, then you would have these 2 electrons down here. That would be where it would go first. The third electron could no longer fit in the 1s because the maximum is 2 electrons. Therefore, you would have 1 electron up there. So as we continue to add electrons, they would appear a second electron in the 2s orbital, and then you could fit 6 electrons into the 2p orbitals, and then up until 3s, etc., etc., etc. Again, and in organic chemistry, we seldom stray past 1 or 2. This is where n is equal to 1. All right, that's the first shell, and n is equal to 2, which is the second shell. All right, so one of the really important things to note here is that there is a maximum of 2 electrons, and the n is equal to 1 shell, and there is a maximum number of electrons in the n is equal to 2 shell of 8. And this comes from the fact that you can fit the maximum of 2 electrons in the 2s and 6 electrons in the 2p. Therefore, 6 plus 2 gives us those 8 electrons. We say that this is an octet if that guy is full. Octet, just like in music, 8. The octet rule is going to be very, very important in any time that you are looking at an n is equal to 2 shell. So this is a partial version of the periodic table that's found in your textbook. If you look up in the back of your book, there's a full periodic table, but this is the main part of the periodic table that we deal with in organic chemistry. There are some exceptions to that, but for the most part, these are the major players. All right, so this very top row here, the very top row that you see right here, that just has hydrogen and helium in it, in general, what those guys are the atoms that would have the electron configurations corresponding to a shell of 1. So these guys are in 1s. Hydrogen has 1 proton. That is the definition of hydrogen. Therefore, a neutral hydrogen would have 1 proton and 1 electron. The electron would go into the lowest energy orbital, which was the 1s. Since there would be only 1 electron, we use the electron configuration sign of 1s1. 1s being the orbital, and 1 being the number of electrons in there. All right, so for helium, which could have that second electron still in the 1s, its electron configuration for neutral helium, that is to say it's got 2 protons, therefore it would have 2 electrons, would be 1s2. The electrons don't have to go into any higher orbitals because they're in their ground state, that is to say they're in the lowest possible location, which would still be in 1s. All right, if we went back, basically that would just be those up and down arrows, the first pointing up, the second pointing down, both of them in the 1s subshell. All right, the 1s orbital. So when we move past those onto lithium and beryllium, what we're looking at is atoms number 3 and 4. So lithium is atom number 3. That's right here. And beryllium is atom number 4. You can find atomic numbers. They're written in the periodic table. They're not written in this one. So lithium, neutral lithium, would have 3 protons. Therefore, it has 3 electrons. So for lithium, you can't put all 3 electrons in 1s. Therefore, the electron configuration for this guy, the first 2 electrons would go in 1s. So it would be 1s2. And then the next electron, that only leftover electron, would have to go into the next highest orbital, which would be 2s. We'd only have 1 electron left, so this guy would have 1 electron in the 2s, 2 electrons in the 1s, therefore 1s2, 2s1. All right, moving on to beryllium, it would be 1s2, 2s2, etc., etc., etc. All right, the major player in organic chemistry is carbon. Carbon is located right here. If we count them through, you'd see that it has the atomic number of 6. So, carbon has 6 electrons. All right, and they would fill, the first two electrons, as always, would go into the 1s. Therefore, it would be 1s2. The next two electrons could go into 2s, and that would be 2s2. And then you've got two more electrons, because neutral carbon would have 6. Therefore, the next two electrons would need to go into the next highest energy orbital, which would be 2p. All right, and then this would be 2p2. So we would indicate a neutral carbon, which is to say a carbon with 6 electrons, as having 2 electrons in the 1s, and then 2 electrons in the 2s, and 2 electrons in the 2p. So the way that we drew that in terms of an energy orbital would look like this. We've got our 1s down here. We've got our 2s slightly higher in energy, and then our 2p, which remember had 3 different orbitals, would be slightly higher than that. So the first 2 electrons go into 1s, the next 2 electrons would go into 2s, notice that they're always filling from the bottom up, and then the next 2 electrons would go into 2p. They prefer to spread out because electrons are all negatively charged and like charges repel. Therefore, they will always spread out in the p before lumping up together. So the first 2 would go into essentially different orbitals or different rooms in that 2p apartment. All right, so we differentiate these electrons, though, once we move past 1s. 1s, at this point, these electrons down here are buried into what we call the core. All right, core electrons simply mean that they are stuck in the center. So remember, 1s is a small sphere that's stuck at the very center. Those electrons are good, that shell is full, and furthermore, they're clustered close to the nucleus away from the outside of the atom. Therefore, we call those core, and they do not react. Remember I said earlier that the electrons moving around is the important part of organic chemistry. Those reactions involve the movement of electrons. Well, the electrons that can move are those that are not in the core, that is to say, the ones on the outside. So these electrons in the 2s and 2p are called valence electrons. These valence electrons are the ones that can react. So notice that despite the fact that neutral carbon, has 6 electrons, it only has 4 valence electrons. 2 in the 2s, 2 in the 2p. All right. You will notice that in the periodic table, no matter where you find a periodic table, there is an indicator of that this is column number 4. These column numbers always indicate to you how many electrons are in the valence shell, that is to say the outermost electrons that are reactive. All right. So, moving on, let's look at some other atoms. All right, so here we see a very small shrunk down periodic table, but we can start going with the major players. Hydrogen, we saw a second ago, has 1 valence electron because for him the 1s is its outermost shell. So we tend to indicate these electrons when we're drawing out the atomic symbols as dots. Therefore, hydrogen would have 1 dot or 1 valence electron. Likewise, lithium, that's right below him, lithium has 3 electrons. All right, remember we drew that one out, but it's got a 1s2, 2s1. So those 1s electrons are stuck into its core, and it only has 1 valence electron from that 2s1. So this is its valence electron. That's the only one we worry about. Therefore, lithium would also have only 1 valence electron. All right. And once again, we can look at the label on the top of the periodic table. Hydrogen and lithium and sodium are all in column 1A. This column 1 indicates that neutral hydrogen has 1 valence electron, neutral lithium has 1 valence electron, neutral sodium has 1 valence electron. All right, with carbon, which is over here, it is in column number 4, therefore it has 4 valence electrons. When we draw carbon out, we put 4 dots around him for those 4 electrons. We don't worry about differentiating out the s's from the p's, but because there's a 2s that can fit 2 electrons and 2p that can fit 6 electrons, we would have a maximum number of 8, but carbon only has 4 in its valence. So 1, 2, 3, 4. We always spread them out. Probably remember this as well. Lewis structures are drawn as dots around the atomic symbol. And we draw them on each of the 4 different sides. The maximum that we could get would be with neon over here. Notice that neon is in column number 8 because neon has 8 electrons in its valence orbital. If we count out the numbers, neon is actually atom number 10, but the electron configuration is 1s2, 2s2, 2p6. Therefore, it's got 2 electrons in its core, which would be these guys. These are in its core. And it's got 6 electrons in 2p, 2 electrons in 2s, meaning we have 8 valence electrons. And those are the ones that we worry about. Those are the ones that are reactive. So, we will draw all 8 of those around the outside of neon. 1, 2, 3, 4, 5, 6, 7, 8. And those are my 8 valence electrons. Therefore, this would be the atomic symbol for neon. The Lewis structure of neon would have 8 valence electrons all the way around the outside. Once you fill electrons all the way up to a full shell, which would happen in the case of helium, with a full n is equal to 1 shell, it would happen in the case of neon with a full n is equal to 2 shell, and then moving on, argon, which we don't worry about that much. Argon's up here. That would be a full n is equal to 3 shell. Those guys are very, very stable. They have full octets. They have all 8 electrons around them. Therefore, they are not reactive anymore. Once you get past those, so that is to say once we move past neon, which is atom number 10, onto sodium, which is atom number 11, we've gone from something with a full happy subshell to something that has 1 extra electron. So that's where we kind of loop around the periodic table from one row to the next. You get more and more filled shells as you move to the right. Once they get to the far right in the noble gases, those electrons are then full valence shells. If you put 1 more electron in, you've moved to a new valence shell, and the old valence shell would be locked in the core. Thank you very much for your attention, and I'll see you in class.